Hi, in this presentation, I will talk about learning-based traffic reconstruction to autonomous driving. First, I will discuss some of our recent work on city-scale traffic animation and presentation using statistical learning and meta-model-based optimization. Next, I will talk about how learning to drive through visual analytics of accidents using parameterized simulations. Then I will discuss some of our recent work on enhanced transfer learning for autonomous driving using systematic accident simulation. Finally, I'll conclude by discussing and presenting some of our work on robustness in autonomous systems. In the US, the total extra cost for mobility has been growing and was estimated to be about $160 billion in 2014. The cost has been continuing to increase with a little dip in 2008 due to the Great Recession. In addition, the vehicle production has also kept going up, especially for cars denoted using the light blue in these figures. This means that we will have more and more cars on a limited number of road networks. Unfortunately, the traffic problem is only going to get worse. Our world is undergoing rapid urbanizations. In 10 to 20 years from now, most people on this planet will live in cities. That means the cities will become larger and more complex, while the development of infrastructure, such as the road network, is unlikely to keep up the pace. Furthermore, technology has made it worse. Now, because of the ride-sharing company, people have more incentive to drive instead of taking public transportation. In New York City, we have seen a big increase in ride services pre-pandemic. And during the pandemic, although that has gone down, we are also seeing the ride services used to be going up now after the post-pandemic. In order to understand and alleviate the traffic problem, we first need to be able to visualize it, analyze the costs, identify the bottleneck, and test traffic policy through traffic reconstruction. In addition, we're seeing there will be off Earth. And furthermore, there are also applications such as VR system for teaching people how to drive. And increasingly, more and more autonomous vehicles are also learning how to drive through simulations. However, most of these 3D virtual Earths don't have much content. The roads are generally speaking empty. So there is an increasing demand to incorporate realistic traffic flow into these virtual worlds so that more applications, including virtual tourism, network gaming, navigation systems, and urban city design can benefit from it. In the past decade, many important work has been produced to either improve the traffic simulation technique or the visual quality of the traffic animations. The closest work to ours are Vandenberg's, Wilkie's, Chow's, and all these works use largely real-world sensor data to reconstruct traffics. However, these works that I just mentioned, use traditional traffic sensor data that is collected mostly through the in-road sensor data, in-road sensors such as the loop detectors or the fixed video cameras and lasers, as you see here. These in-road sensors, however, while they provide accurate measurements, are mainly installed on the highways, which only constitute a very small portion of the road network in the city or around the city. As a result, using in-road sensors, these prior work are only capable of reconstructing traffic on highways and freeways. Our goal here is to reconstruct city-scale traffic So the question is, where do we find the data? If the in-road sensor data are inadequate? Well, the answer is simple. It's this little device that sits in our pocket. GPS devices has it's widely available, and they are just embedded in mostly mobile devices that most of us carried. GPS data is also the most promising data source to reconstruct city traffic because of its broad coverage. And more projects have been releasing their GPS data sets to the public as well. There are several issues, however, regarding use of GPS data. First of all, GPS data usually contains low sampling rate. This is an issue because during that time, a car can travel multiple road segments, and we only have one timestamp difference between all of them. As part of the reconstruction requirement, we really want the travel time on each one of the individual road segments that's generally speaking not collected on the GPS data. So in order to address this problem, we need a dual solution, that is ability to compute the ability to compute map matching problem and the travel time estimation for each one of the road segments. So what is a map matching problem? The map matching problem is to first map the noisy off-the-road GPS points back to the road network. Here are a couple of perfect examples of the GPS points off the roads. And what we need to determine is, given two GPS points, what is the path traveled by the car? Is it the upper or the lower in this simplified example here? Most of the existing map matching algorithm makes the simple assumption of using the shortest distance. This is a problem because it introduces biases in a congested network. And it's also basically assuming that we have anti-road network and only geometric information is required. This is not true. In fact, most of the navigation systems on the GPS devices use not the shortest distance navigation algorithm. It uses the shortest travel time path. In terms of a travel time estimation, there are also different approaches such as probabilistic, tensor-based, and deterministic algorithm. And what we want to know is how much time is spent on each one of the road segments between two timestamps that we receive from GPS data. Now, if you combine these two together, we can reconstruct the traffic. However, there is a problem. If the map matching algorithm produces the wrong path, this will lead to cascading of errors in also introducing the wrong travel time for each one of the road segments. And this can cascading down the road. Another problem with GPS data is the sparsity of the data. And in addition to that, not only we have the sparsity of the data, that most of reconstructions using the sparse data set also assume that we have sort of static traffic based on the current sparse data that we have. So to sum up, our problem here is, given the GPS data sets, how can we reconstruct city-scale traffic, knowing that we have low sampling rate and sparse data? Prior work using sequential methods will lead to cascading errors. Our approach that differs from the prior work by using an iterative approach, which I will explain next. In regard to addressing the sparse data sets, prior approach also used static interpolation. Our approach, in contrast, will use the dynamic interpolation. Next, I will talk about our approach in more detail. Here is an overview of our approach. First, we assume our input data include GPS tracers and a digital map, possibly with an optional trip records. Part one of our approach is the initial traffic reconstructions. During this initial traffic reconstruction phase, we were given this sparse GPS data. We would estimate this initial optimization step by performing the map matching algorithms using the shortest travel time assumption. And then we would perform the travel time estimation using the statistical learning. We would then iterate between the two steps to improve one another until it converge. When it converges, we would have a fairly accurate reconstruction in area with GPS data coverage. Now, this initial optimization is a good starting point for our iterative scheme, and it gives us course estimation in area with GPS coverage. We can then further improve by the next final optimization process, where we actually also incorporate the traffic flow theories to further improve the results. And it is also the good starting point for the next step, which is the dynamic data completion step. From the previous step, we have partially accurate reconstructions of the traffic in area where we have GPS data. However, there are areas that we have very sparse or no GPS data. So what we do is that we use the traffic simulation to fill in the gap. We assume that we have partially accurate reconstruction of traffic. It's accurate in area with GPS data coverage due to our iterative process, but it is inaccurate in area that we don't have GPS coverage, where we need the bi-level optimization. The output is a fully accurate reconstruction. We basically introduce the traffic simulations model in the second stage, where we will use the traffic simulation to fill in the changing traffic, dynamically filling the gap in area where we don't have a GPS coverage. On the boundary of this area where we don't have enough GPS coverage, we will use GPS data that was made available to us. So they basically set the boundary conditions. And essentially what we're doing here is a simulation-based optimization. We have a meta model that is a deterministic function to replace a stochastic simulations. And this is the equation that we use, as you could see here. We have essentially a set of decision points that we need to make that will consider all the turning ratio in the simulation area. In this meta model, we also have the road network specs as highlighted here. And we also have parameters that we can iterate and improve in this meta model that will capture the traffic flow. The traffic equation will essentially serve as a physical component for this meta model, as well as this quadratic polynomial that you can think of it as a fitting model to fit the data that we have to the traffic simulation. One of the decision points that we have to make is at every single intersection points, we need to determine how many car will go straight and how many car will make a turn. And so this is a turning ratio in a simulation area. This is part of our meta model parameters, and that we will iterate through the process to improve based on the data that we have and the simulator that we have. Once we have done all this iterative process, we would then have a refined traffic simulations that will take into account some of the decision point regarding the turning ratio at every single intersections. We will then evaluate these decision points and incorporate it with our traffic flow simulations and traffic equations, and using a full-blown simulations to fit these meta model to the traffic data or the GPS data that we have. And we'll iterate through this whole entire process until it converges. So in the initial traffic reconstruction, we compare our approach on the road match, the map matching algorithm to prior work. We found that our technique achieved the lowest error rate up to about 97% relative improvement in accuracy, when we incorporated dynamic data completions, the second stage of optimization, the bi-level optimization, we further reduced the errors down to about 7.8%. So the average speed up overall is about about a factor of 36 times faster. And the highest speed up that we observe is about 90 times faster. And here are sort of some of the diagrams that I mentioned earlier. For the map matching algorithm, we observe about 97% of relative improvement in reductions. In terms of overall performance, using dynamic data completions, we were able to achieve about an average speed of about 36 and the highest speed up about a factor of 90 times faster. This approach allows us to visualize the traffic reconstructed for different areas, as you can see here. And we can also produce city scale animation as well. It enables us to dynamically interpolate missing data that we don't have from the GPS data. Our reconstruction also enables modeling and visualization of city scale traffic. The approach that I presented here, it's not only useful for traffic simulation, but it can also be used for multi-agent system as well. Particularly, it generalizes quite well to other domains, learning from mobile sensor data that could be used to track school of fish, flocks, birds, or insects. And it accelerates local fitting as well as large-scale motion reconstruction. Next, I'll talk a bit about driving through, learning how to drive using visual analytics of accidents based on parameterized simulations. This work was presented at ICRA 2019. So the basic motivation here is that training data collected by human drivers are largely safe for training autonomous vehicle. So these self-driving cars would not know how to deal with scenarios that could be challenging. And humans are needed also to label these data, which is inefficient and also error prompts. Nearly all the end-to-end systems are limited to mostly lane following. So human is needed to take control when the lane is changing, which can be very demanding, especially in cases when there are other obstacles present. So the goal of this project is to develop an end-to-end control policy that can model temporal sequences and process input from a single front-facing camera to perform both normal driving and collision avoidance. Our approach is based on the use of a simulation platform with parameterized environment setting, grounded in transportation engineering and accident analysis, which I will talk about in just a few minutes. Accident analysis systems developed by us is based on a probabilistic multi-agent simulation to generate and annotate data. We, in addition to these features, we also used a novel memory-enabled control policy based on LSTM and CNN architecture to continuously steer an autonomous vehicle and avoid collisions. Here is a system diagram. In this systems that we introduced, you will see it consists of the three modules I just mentioned, the simulation platforms, which would assume that we have the environmental factors, the real-world road network. Then we perform parameterized simulation based on these environmental factors. The middle module perform the accident analysis, where we actually use our multi-agent collision avoidance system that is generalized for arbitrary agents. It allows us to simulate car following the lanes and also perform collision avoidance. It makes certain assumptions regarding the fact that we have a front-facing camera, and it also assumes that we have some of the simulation specs, or we can learn from it. Lastly, but not the least, is that we have a learning module which will perform road condition classification and learn how to steer based on various factors and develop a control policy for steering and driving. So in this particular systems, one of the most important element is the multi-agent simulation system, which is based on a very novel algorithm that we developed called. And broadly, the previous work on walk drivers allow us to essentially compute the probability of a colliding with neighbors given an agent at each time step. It attempts to decrease these probability as it navigates through time and space with certain level of assumptions. The base walk drivers originally was intended and developed for handling crowds, human crowds, with uncertainty and nonlinear motion model. It has multiple mechanisms to deal with nonlinear motion model, and it assumes dislike agent with no dynamics or kinematic constraints. The new generalized walk driver, however, works for arbitrary 2D agents with uncertainty, also nonlinear motions, but also different shapes with dynamic and kinematic constraints as well as path constraints. So let's take a look at what the system can do, as you could see here. This is a car driving through with avoiding multiple moving obstacles, the blue cylinder. You can see the car is not a disc-shaped object. And you can speed up and slow down, and also make turn, which is a linear motion here. And you can also accelerate. And it can decelerate as you run into dynamically moving obstacle like the blue cylinders that you see here, and driving on the curvy road and turning with different velocity and accelerations. And here is in a much more open scenario off the road, where now you see there are multiple cars and also multiple agents. And these cars are not just cars, but also buses interacting with each other in a very open environment with multiple agents. So this novel collision avoidance algorithm called generalized walk drivers also taking into account uncertainty, and it performed collision avoidance very well. Most importantly is that when it does the collision avoidance, it actually also the algorithm also gives us the collision and contact points. And this essentially provides an automatic mechanism for data annotations on the path that the vehicle travels. It then gives us ability to pass this information to the autonomous vehicle to learn how to steer away from the obstacle using these annotated data points, and to detect road conditions and various risks and hazards on the road. So next, I will briefly talk about the memory-enabled control network. This network consists of an LSTM CNN architecture. The LSTM handles the temporal sequence, has about 100 hidden units, about 5 frames per samples, and it has many-to-many sequences predictions. CNN handle the single front camera image inputs. We assume that the input will consist of 320 by 160 times 3 images. Use a VGG16 network setup. Output a steering angle telling us how to drive and steer the car. Here are the results. As you could see, that the resulting trajectory show how the car avoid the obstacles, and it also have multiple roads options to steer these obstacles. Here is the video showing how our system works. We compare our methods against a baseline, a recent driving simulator by Wksp from 2016. And you can see when we started, both our simulator and Wksp ran into the pole. Now, in this simulated accidents, our model actually learned that what to do. It actually annotate automatically using our algorithm, where are the contact points and what are the dangerous road conditions. So when it encountered again, it would know how to avoid it. In contrast, Wksq's 2016 approach doesn't know how to do it and will run into the pole again while ours avoid it. Here is a generalization of our approach to different type of obstacle, not just poles. And again, you can see it successfully avoid all different type of obstacles. You can also look at the trajectory comparison here, and you can see how it avoids different type of obstacles. And not only it's able to avoid the obstacle, we also know how to drive on the road better, where Wksq's approach would often drive off the road, ours will stay on the road much longer. And again, you can see the trajectory differences when they encounter different obstacles right here in these 4 different scenarios. In addition to obstacle avoidance, our systems also enable simulations of different kind of environmental factors, such as rain that you just heard, also snowy days, under different road conditions, more slippery conditions, foggy weathers, and so on. And also different lighting conditions, different darkness, different brightness. Okay, next I'm going to talk about enhanced transfer learning for autonomous driving with systematic accident simulation. Next, I'm going to talk about enhanced transfer learning for autonomous driving using systematic accident simulations. The motivation of this work is to perform end-to-end learning for self-driving car. And we want to show that the imitation learning is effective for training an autonomous car. However, self-driving car can suffer from poor generalization for corner cases. So we overcome this inefficiency and this inadequacy by using accident data sets that are simulated for training self-driving cars. We explore the idea that virtual world training can in fact complement real world training and have more diverse applications. Our objective is to establish a systematic approach to generate accident data from pre-crash scenarios defined by National Highway Traffic Safety Administrations to improve the steering wheel predictions using the state-of-the-art end-to-end learning model to improve its efficiency and then extend it to policy gradient approach. We also proved that simulation data can indeed be used to extend the real-world driving data to train the imitation learning model and overcoming the limitation of inadequate real-world data. The sets of accident scenarios that we simulated and the sets of corner cases we were able to capture through our simulations are based on the reported scenario by the NHTSA. These are the sets of scenarios that led to the maximum number of accidents. These accident scenarios are simulated in the virtual world and modeled by Unity game engines based on pre-crash reports. The data on braking forces and lane changes, distance, and vertical offset leading to collision are generally speaking very limited. But however, through the use of a Unity game engines and a simulation engine, we are able to capture those. We sample these parameters over some normal distributions with averages centered around the typical driving behaviors, as you could see here. So basically, we design, implement these different scenarios. We have these different sets of parameters that you see in B, and then we sample the sets of parameters using a normal distributions around some average value. These might including the car mass, the vehicle's travel speeds, and so on. And then we use these variation of the sample data to generate a large number of simulated accidents scenario for training the car. Next, you can see...
Following these slides will be examples from the accident simulator along with trajectory prediction results from transfer learning.
So here are sort of different scenarios that are simulated with our engines. And here it's a head-on collisions. So again, those who are very similar setup will just change a few parameters, sample a different parameter. Here is driving onto the other lane with the head-on collisions. And again, this is a slightly different variation of that. And here it's a slightly different examples. Again, running into the other lane.
And right camera views are also able to be generated.
So in addition to lane changes, we also have dash cam camera view, either from the passenger side or the driver side as well. So these kind of give you some idea of what different viewpoint can be captured using our systems. We have incorporated this with application to real-world data sets for trajectory predictions, and you could see that our steering angles is by and large pretty much match those of the captured steering angle and that from the actual real world driving.
Following these slides will be examples from the
We perform some comparison using 3 different models. Model 1 is train a learning model using the simulation data. Model 2, train this learning model using real-world data. And Model 3, do the training on the model using real-world data, but also learning transfer from Model 1 that use simulation data. We have shown in our comparison that Model 3 generalizations, which is based on the real-world data, but also transfer learning from Model 1 that use simulation data, outperforms Model 2 that is trained purely only on real-world data in terms of improvement on collision avoidance and general driving behaviors. The network architecture is shown here. We collect the demonstration trajectory from expert, treats the demonstration as independent state action pairs, and we learn the policy using the supervised learning by loss functions. The network has an image input, as you could see there, through the stack of convolution layers and fully connected layer, and output the weights. These weights are then transferred from the simulation-based learning model to a hybrid model that uses both the real-world data and the transfer weights. We compare our model against the baseline. The baseline model generally deviates much more from the ground truth steering angle than ours. And in fact, you can see that our methods was able to complement the real-world data by using simulated accident data transferred through the simulation-based learning. And the blue bars are the baseline errors, and the green ones are ours, which is generally speaking much lower. In addition, we also show the loss convergence, the baseline versus our model. The baseline model is in blue, and the green one is our model. And again, you can see that the loss conversion methods using our transfer learning methods achieve far better convergence. Here we see the results of our learning model. you could see we actually have a car here that learned from our transfer learning methods, and it's actually trying to overtake this other blue car here. You can see that it's successfully do that, and it will continue on the road and drive. The next scenario here is you will see approaching is this car will then try to overtake the two cars ahead safely and successfully. The road is curvy, and so the car was able to even overtake the other cars while it's driving up on the curvy road. And now it's going to attempt to overtake the second car as well. And again, it safely and successfully overtake the second car. So the conclusion is that we see through these examples, virtual data or simulated data can indeed be used to complement the real-world driving data. Transfer learning can help overcome the lack of real-world data for corner cases and accident scenarios. We see that training self-driving car using transfer learning and simulated accidents can improve the learned driving behaviors and collision avoidance. Next, I'm going to discuss how to improve robustness in autonomous systems. This is a recent work that was just presented at ICRA this year. Recent advances in machine learning and computer vision have made it possible to do end-to-end training for tasks like semantic segmentation, object detection, steering angle predictions for autonomous driving. However, computer vision models are also known to be susceptible to domain variation. That is, the real input data at deployment may not be from the exact same distribution as the training data. And you can see some of the examples here in this particular images. Here are just sort of 5 images of the same goldfinch bird, for examples. And you could see clearly that there is a different appearances in terms of the images, even though it's the same bird. And as a result, the classification also the classification result also varied depending on which images, even though it's the same images. So this is the well-known robustness problem for neural network. So how can we address that in autonomous driving systems in scenarios that where we would observe some domain shift that can occur naturally in autonomous vehicle, say due to either external issues such as weather, like the snow, the frost, the fog, or the internal factors such as the lens distortion, the motion blurred, the pixelations, and other kind of JPEG effect that you observe here. To alleviate this problem, some of the previous work proposed training neural network on more data. Effort has been made to collect more data with different domain shift and also more complicated traffic scenarios, either real world or synthetic world data. In this work, we consider a more adaptive but less expensive approach by introducing the idea of adversarial training to autonomous driving. The formula of adversarial training is essentially a min-max optimization problem, where the inner maximization finds perturbation to the input data that cause the model loss to increase, and the outer minimization adapts the model to the adversarial input perturbation. Model trained with this procedure demonstrate boosted robustness against imperceptible input noises, also known as adversarial attack. However, instead of adversarial attack, we actually care more about robustness against some of these natural domain shift that we observed. So for these purposes, we introduced and modified this network a little bit by using the idea of adversarial data augmentation, which simulate the domain shift in the input data, as you could see here. With this approach, we can choose a set of differentiable image transformation operation T and parameterize delta, as you can see in the formula, and optimize the delta by using a gradient descent to produce adversarial data augmentations. For example, a possible operation, a transformation operation, can be Gaussian blur, and its parameter delta can be the sigma of the Gaussian kernel. So we can perturb delta to introduce various level of perturbations. And we show these two different processes of introducing adversarial perturbations and using the same concept to introduce the perturbation to the input images and thereby performing adversarial data augmentation on the lower level. Here is an overview of our proposed framework on adversarial differentiable data augmentation. So given a batch of input images that you see on the left and the sets of augmentation operation T1 through Tk, each of the augmentation will be optimized in the adversarial process to simulate a worst-case domain shift through our adversarial data augmentation process. Then the learning process train a network model on our augmented data through stochastic gradient descent, or SGD. A shared backbone network is involved in both process and then being updated after each one of the learning. And this is going through this sort of batch feedback loop continuously. So now let's take an insight of our data augmentation module. For each one of the input images, we optimize the augmentation for multiple steps. Since the operations are differentiable, we can directly update them with the gradient feedback from the downstream model using the protected gradient descent, or PGD. The projected gradient descent, or PGD. The augmentation gets more and more adversarial after each one of the PGD steps, And after several updates to the input, the model itself will be updated with the final version of the augmented input. In this diagram, X hat is the final output of the augmented input using this adversarial process that we just mentioned. We conducted our experiment on the task of end-to-end learning control of the steering angles or the steering angle prediction. The bottom panel shows 8 basic image transformation that are used in our experiment, along with illustration of a different degree of a severity in terms of perturbation controlled by alternable parameters. As you could see in the 3 rows, the lowest is on the top, and as it goes down to the bottom, the severity and the level of perturbation increases. And you can see also the quality of the image degrade much more significantly as you go down to the bottom. We show the result and compare our method with several other baseline techniques using data augmentation. We evaluate the accuracy on the clean data and the error rate on image degradation. And the detail of the evaluation matrix are available in our paper. But I just want to highlight here that we consider 3 different test scenarios. The first is the individual transformation applied to each one of the factor, single perturbations. Then we have a combination of multiple factor being perturbed. And lastly, we have unseen factors that we don't currently have in our current existing sets of synthetic images with different unseen image degradation. We obviously also have the original data sets. And on all these data sets that we consider, our methods demonstrate the highest level of improvement over the baseline model. In addition, you can also see specifically our performance on the unseen image degradation. You can see that our method consistently improved the accuracy of a model across different data sets, whether it's Honda, Solid, Chanfang, NVIDIA data sets, or Audi data sets, on all type of degradation, that unseen degradations, including degradation due to snow, frost, fog, or distortion and motion blurs and zoom blur and pixelations and JPEG. We have extended the approach I presented here to gradient-free adversarial training against image corruptions. This most recent work will be presented in Europe this year.
This is a supplementary video for gradient-free adversarial training against image corruption for learning-based steering. We have several motivations for this project. For safety, autonomous vehicles need to drive under varying lighting, weather, and visibility conditions in different environments. Internal and external factors can pose significant challenges to perceptual data processing and affect control and decision-making of autonomous vehicles. And because of the points highlighted above, our goal is to harden neural network systems against image degradation and improve robustness of learning algorithms. Our target task is learn to steer in end-to-end autonomous driving. This includes perception and control. This task can be observed in the diagram, where a network predicts a steering angle with image input. Our primary key contribution is a scalable training scheme to improve robustness of autonomous driving against image corruption, while increasing overall accuracy of learning-based steering with adversarial data augmentation. It is among the first to train on single image perturbations while improving overall performance on functional combinations
In summary, I have presented learning-based approach that use simulation data to perform citywide traffic reconstruction using statistical learning and meta-model based optimization. I also describe a probabilistic model for unified collision avoidance for autonomous vehicle and pedestrian in a mixed environment. And I show autonomous driving and control can be performed using image-based analysis of simulated accidents. I also show that transfer learning using systematically generated accident data can in fact improve the overall learning for autonomous driving. And to conclude, we show adversarial training using augmented simulation data to improve the robustness and the generalization of the systems. There are some issues associated with our. I want to end and thank the sponsor who made these works possible, as well as my collaborator. And I'll take any questions. Thank you.